one is 渡辺君、関さん、チャンさん。And members of used to are Oscar, 五十嵐君、まやちゃん、山岸君。So, first presenter is group one. Please start. presentation for each presentation time for each group is 90 minutes, and it's including Q&A. Please start.
Hello everyone. Today our group would like to talk about this book, or chapter 1, 2, 3. First, preface. This book is a practical guide to the exploration and understanding of social and economic issues through simulation, written by Deguchi Lab and Clancy in September 2004. I would like to talk about chapter 1. This slide shows chapter 1's outline. First, the first example of using computer simulation was data from the 1960s, but simulation began to be used widely in 1990s. So simulation is rather a new idea. Simon said by the emergence of complex behavior from relatively simple activities. So simulation introduces the possibility of a new way of thinking about social and economic processes. Have a question? It's right. Social scientist. Simon Gilbert. Yes, Simon Gilbert. Yes. Sorry.
So, what is the meaning of a new way of thinking about social and economic processes? What is new? New idea, new way. You can explain about that?
Next slide.
Okay.
Purpose. What does type of problem and purposes for which simulation is specified? Present a few examples from next. What is simulation? Simulation is a particular type of modeling. This modeling model means a simplification of some other structure or system, smaller, less detailed, less complex, or all of these together. Example, airplane. This picture shows a real airplane. So simplification model. This is a toy airplane. This way, our model airplanes recognizably an airplane. Simulations mechanism. Simulations have input and output. Input entered by researcher. The attribute need to make the model match up with specific social setting. Simulator で observed the simulation runs, the behavior of the model through time. So this slide shows an example of simulation from now. When I am looking for a marriage partner, if I must be dead. Now here, I'd like to talk about the mate researching game example. First, all the number are not visible. I can't see all the number. Second, we will reveal the right and from top left. Next. And second line. Open. This number shows varies citability score. Girl 1 citability score, girl 2 citability score, 3, 4, and when this the last decide for myself when I want to stop. The last number, stop number, if 308. This number shows citability score. My purpose is the best strategy of maximizing the score while minimizing the number of partners I have to date. Date number minimize this citability score maximum. This way shows the simulation.
How is the score is chosen and decided?
Themselves, if I decide number, I think max number. I don't know the next number. I think 55. No, 100. No. Maximum.
The scores decided randomly.
Yes, random.
Table of this table. How this table?
This table shows simulation 1. Simulation 2 the random numbers. Each simulation number of tables. Not same number, same table.
What do you want to know by the simulation?
Sorry.
What do you want to know in the simulation?
Social system. The searching, mate searching. I want to show by simulation.
Okay. So in the previous slide, we showed that simulations have to have some inputs and outputs, right? So in this example, what is the inputs and what are the outputs?
Input. My decide the number. I decide to choose number. Numbers timing. Input. Output this citability score and date number of days. Strategy is strategy.
Table
Using
Yes.
Okay. Thank you.
Table is input.
table is input, and then the output is the
Oh,
suitability score. That means after how many days you will get married. So that's the output.
そう設定なのか。
How many times you have to date to get married to a
Yes.
I know. I know about this simulation, but I think input is strategy. So as Yagisa says,
I think both of them is input, I think.
Strategy is kind of action. How can you input strategy?
but we should decide the strategy. So why it isn't it?
So the
Input.
input is the table, and then according to the strategy, you will choose the number. So that's kind of input, but
In the simulation, the various table is such. We search various table. Many kinds of table we search in this simulation.
no, only this kind of random table.
So
That means before you go to a date, you don't know how much you will be with this man, right? So that number is random. And after this date, you will not know how is your next date. So you cannot see the next number. So after a few days, maybe you are tired and maybe you think, oh, this number is good enough, then I will stop here and I'll put a number.
I know, I understand about this game, but I can't understand why strategy is not input. No, it's okay. Okay.
So yeah, I think that the game itself maybe is very famous and all know about this game, but we have to look this game as a simulation. So what is the inputs, what is the output, and what is inside the model.
Yes.
So yeah, we have to look is as a model, as a simulation. So that's the point, I think.
The use of simulation from the to obtain better understanding of futures of the social world. But this is not the only value of simulation. First, to look into the future. Example, the use of simulation in demographic research. Second, to develop new tools to substitute for human capabilities. Example, expert system. The systems emulate the decision-making ability of human experts. So be used for the training of geologists and train pilots. And etc. Discovery and formalization. Social scientists increasingly interested in computer simulation to assist in formalization and discovery. There are several reasons why simulation is more appropriate for formalizing social science theories than mathematics. Computer simulation. Simulation is computer simulation programming language. The merit: first, more expressive and accessible to non-specialists. Second, deal more easily with complex processes. Third, has been modularized. These 3 point examples in chapter 3 and 6. simulations, the relevance of simulation to understand human societies. Example, if one agent set simple rules, but the or behavior or can become extremely complex. So this slide shows cannot be understood by conventional statistical models methods. So the occurrence of new interdisciplinary field called complexity theory. Complexity theory, interdisciplinary field proposed by Wadler, Kaufman, Solar and Goodwin. The theory is developing general results about a nonlinear system. Example, stream of sun. The middle shape, the angle of the slides. The angle of the sides are predicted, but the timing, location, and scale of the landslides are unpredictable. So even if we had a complete understanding of the factors affecting individual action, this would not be sufficient to predict group behavior. So emergence comes from complexity theory. Emergence is the interaction of multiple complex two organs. From the behavior of individual elements cannot be predicted that such a system is configured. Example, temperature. An individual atoms has no temperature, but a collection of them, this or one, have a temperature. Example. So example is emergence is one of the most important ideas in order to simulate.
I'm sorry, I have a question. In the sunslide model.
Sunslide?
Yes. Yes. How can you know about the effect of sunsliding in this model? I can't understand. I couldn't understand.
Okay. Can predict predictable. The sides are predictable. Sides, the angle of sides なので、
あ、日本語でも
要素を理解しても全体にはその予測できないことが起きるっていうものを表していて、これだったら土砂崩れなので、砂が積み重なる角度はその単体同士の作用なので計算で求められるんですけど、それがもう上からずっと溜まってくるといつその土砂崩れが起きるかは分からなくて、で場所も規模もそれは確実には予想することができないっていうことを。
あ、この理論は複雑性理論っていうのは
はい、
分からないっていうことを言ってる。分からないことが起きるっていう。
そうですね。そういう今までは、これ前までのスタティスティカルメソッドっていう考え方の時は線形であるっていう、砂が同士が集まったらそれはもう全て予想できる線形に依存する、出力があるっていうことが言われてたんですけど、それにとどまらないかもしれないよっていう考え方がコンプレックスっていう。
そういう場合もあるっていうことを。はい。わかりました。ありがとうございます。
This is from the textbook. This example.
This example, stream of sand. Yes. And this picture I choose Google images.
Maybe this model is famous for the model of power law. Do you know power law?
Power law.
Power law. The size
Power law.
the size of a landslide follows the power law.
パワーズオブ
Power law. べき乗則。
何のべき乗則？
大規模な地滑りは非常になんだっけ確率が低いんですけど、稀にだけども
あ、確率の
確率と
あ
要するに地滑りの規模が要するに指数べき乗則に従ってだからでっかい地震はめったに起きないけどもいつかは起きる上限はない。そのモデルとしては有名なんですけど。複雑そっちのと結びつくのかちょっと疑問だなとは思ったんですが、そうかパワーローは知らないですか？
もう記述されてなか
あ、そうですか。
ここにもで僕の知識としてはなかったです。
むしろパワーローとの関連としては有名ですよね。その地滑りモデルは
発生する確率がそのパワーローに従って
まあそうですね。規模と確率が要するにべき乗則に。
これは発生する
そこまで細かくしないからって単に予測できるほどできないものっていうのだけで載ってた話が違いましたね。
去年の発表となんかちょっとうろ覚えなんですけど、砂の山をガーって積み上げていって一粒ずつ粒を落としていくときにいつ起きるかわからないみたいな崩れるのは説明聞いたと思うんですけど、
そのモデルでね、セルラーオートマトンかなんか、
こういう感じ。
そうビガランドスライ
これがサイズ。
オカズ。
これが確率で両方ロックを取ったら直線になるよっていう、まあパワーローの確率分布の。
Maybe this is related to earthquake.
I will research.
こういう超細かいモデルはすごい四国言葉で解いたら解けるって言いますよね。
まあ何をで解くするかによるね。
Last conclusion. This chapter 1 is simulation is well adult developing and exploring theories concerned with processes. Second, it can help understanding the relationship between attributes and behavior of social groups. This table shows next chapter's outline. Continue to chapter 2, simulation as a method. It's all.
Where is this table? It is in the chapter 1.
Yes.
I just don't know why, because we have not know about what is agents. So there's no explanation about agents, so we cannot understand this table, right?
I think it's at the end of chapter 1, so kind of outline what is going to be taught in the following chapters.
It's all.
You have any question to him?
Hello everyone. I will talk about chapter 2 and give a short brief about system dynamics. The chapter 2 can be divided into two parts. The first, the logic of simulation, and the stages of simulation-based research. The first one. When we want to recognize a phenomenon, we
we must get a target. What we want to research, such as if we want to research a market, the market include the suppliers and purchasers. We get a target to research the development of this target, maybe this market, maybe the consumption or the supplement in this market. And from the target, we get a model. The model must have the two characteristics. The first, the model must be dynamics. As is known to all that, the phenomenon is varies in a big way by the time. So the model must be dynamics. And the second one, the model depends on initial conditions. We can set a statistic model or the simulation model. In our life, we always choose the second one, simulation model. We compare the statics model and simulation model. Compare with the two graphs. In this part, they're different. For the statics model, they want to get a predicted date, but for the simulation model, we want to get the simulated date. If we want to set a statistical model, the first we abstract the social process, especially the phenomena, to get the model, and estimate the parameters to get the predict data. But for the simulation model, this is the stages I will introduce as later. The difference between the statics model and the simulation model is the aims and focus. We know that for the static model, they put the emphasis on the prediction or in the result. But for the simulation model, they put emphasis on the precise. For example, such as
excuse me, please speak more slowly, please.
What?
More slowly, please. Speak more slowly, please.
Speak more
No.
slowly.
Too fast.
I can't.
Because I catch cold, so my throat is not.
I'm sorry. I'm not a big
For the statics model, we want to get the the difference between the statics model and the simulation model is aims and focus. For the static model, we want to get the prediction result. But for the simulation model, we want to research the process. This is clear. For example, like a market, when we want to describe a market, if we set a static model, maybe we want to predict the number of supplement and consumption. However, for the simulation model, the more we want to research is the variables happening in the market, why the result happened.
In simulation,
Here.
I think the aim of simulation including prediction.
So that is what I want to say. The difference between them are not hard and fast. They can, but not means they put the emphasis on it.
What is the meaning of fast?
Actually, from my opinion, the statics model and the simulation model, there is no clear boundary between them. But in the extreme case, maybe we think that they're totally different, but the difference between them are not very clear. Maybe I can use a graph or maybe this is statics model and this is a simulation model. This part means it's not hard. They have the same part. This is hard, I think. But in the extreme case, they're totally different. But because the difference between them is not it's not so clear, so it's hard. It is not fast. Here, because this comes from the this comes from the book, so I just explain it from my opinion. If you have some questions or have another ideas about it, please.
What do you mean without mechanism?
Without mentioning them. I mean that for the statics models, we can got a lot of parameters. In the statics model, the most we want to emphasize is the relationship between each parameters and each variables. So for each variables, we prefer a continual equations to describe it. So this is why, without mentioning them. Actually, in the reality, there is no continual models in the reality.
I think we also use parameters in simulation.
Yeah, so I think what is the difference between them are not hard and fast. We can use it. That means we must use it.
Oh.
これなんか
Why are you?
日本語で言ってもいいですかこれ。
いやいやいや、なんか2つの違うが。
まずこの一文を日本語で言い換えてもらっていいですか。この文面白いかな。ハードと
Okay, basically, I'm just checking here. Hard and fast is an expression in English, and it means firmly established. That means that you can say that they are different, but you can always argue that. So like this, like sometimes statistics is used for meters, but they are quite similar. But so that's
So it means similar.
Not hard and fast means not firmly established.
Establish?
Like you can propose, you can try to explain the differences, but there will be always problems.
In the textbook side, we cannot draw a hard and fast line between the two parts. That means we cannot distinguish it so that operators.
So the boundary between both of them are not clear. They also can realize the prediction and to recognize the precise, but not means they put the emphasis on this part. They can do it, but not means they want to. They have both of them have the ability to prediction here. But for the first one, they want to get the prediction. But this is not the aim for the simulation model. Yeah. できるとか、これをやりたいとか違います。
境界が曖昧で。
境界が曖昧なのは分かるんですけど、じゃあなんでわざわざこの2つに分けるのかなと思った。この後もうちょっと細かく分ける。
Because they're totally different models. For the statistic models, this is a macro model. But for the simulation model, this is a micro model. This is also what we want to talk in our life.
The purpose of statistics is to try to find the correlation between the variable and something you want to model. So it focuses on the relationships, not the mechanisms, not the structures. But for the simulation, actually we focus on the process. So we can build the mechanism, build the structure in order to reflect some phenomenon. So the linear relationship is not that important. So that's the major difference between statistics and simulation. So in many cases, depends on your purpose, you may use different ones. There is no strong difference between these two models, but they have different purposes. So that depends on your own research purpose. You can choose different ones.
Thank you very much.
So I think this explanation is totally clear. So the stage of simulation-based research. First, we design a model and building a model, identification and validation, in the end, verification. As is not to all, every model is a simplification. When we want to set a model, this is a process to find the balance point from the abstract and details. For example, when we describe a motion, the most abstract model as is not to all is the average move. But we know that this is not existed in the reality. So we use accelerate speed. We accept that the accelerate speed is a constant variance. This is more complicated than the first one, but in reality, it is also not exist. So the more complicated one here, we describe the motion more detailed. Compare with the abstract and the details. The more the model, the more the abstract the model is, it is more easier to understand the phenomenon. Such as this model, we just want to know the speed, but it is not reality in the. It is not appropriate in the reality, so we need a more detailed model. More detailed model, it is accurately describe the reality, but we know that we can't solve these problems in many cases. So the problem for us is to find the balance point from the abstract and the details. We assume that this is a balance point we want to find. How we can get it? We have two ways. The first, we can get it from our skills, experience, research scale, and amount of data. And the second one, we can set up an artificial society, like a simulation to get this balance point. The next one, building a model. We must use a computer program to building a model. For building a model, we have two methods, using a package or start a fresh writing. There is no doubt that a lot of us have used a package to setting a model. It is more available for us. If we want to set a model, it helps us to encounter a lot of difficulty to set a model. But we know that for using a package, it is not available for all the case because the word is varies all the time. We can't use a package. We cannot use a package for all the case. So we must start an average writing. So this is a problem. Which programming language we can choose to realize our model? What is the best language? From the first to this one, that all the requirement. What is the best language? If we want to set a model, we must to realize the 5 items. The first, well-structured and long-for incremental refinement, along easily and rapid debuggings, with good graphics libraries to process a lot of data into a manageable form, efficiently run and widely used in simulation contexts. I think it's not hard to recognize it because all of us has write a lot of computer programs, and we must choose when we want to select a best language, we must notice the 5 items. So what is the most common language? We always use Java, C, C++, or OC, Perl, Smalltalk, and Lisp. Next, verification. Once we set a model, we must use verification and validation to check whether this model is appropriate or whether this model is correct. What is verification? The process of checking that the program does what it was planned to do. In the verification, I want to ask you to notice the 2 parts. First, the computer often tells us bugs. It cannot run your program, but programs can be run with mistakes. So it's hard for us to check whether your model is right or wrong, just in the program. The next one, many simulations include random numbers generators. Be careful about randomness or probabilities in the programs. For the method of verification, we will talk about it in chapter 9.
Why we have to be careful about randomness?
Because there are a lot of random numbers.
random number generated by some method or laws.
And probabilities.
Randoms and probabilities. Maybe you can think from my opinion. I think that they talk the same things. We must encounter a lot of things that random happens. For example, if they start like this one. This may be a noise. And we set a model, we got the input and the output, but this part we can't, is not predictable. It varies in every step, you know. So we must, so for the verification, whether this model is right or wrong, it just depends on the X, Y, not depend on this part, right? So
Output also depends
yeah.
on noise.
For the it depends on the noise, but you know that if you want to set a model, the most things we want to focus in the input and the output, but for the model there are a lot of noises. This that random happens in every steps. For checking the model, because the varies in every steps, it's hard for you to check X and Y, because every step you just can you just can be conscious the X and Y, not the noise. It is not predictable, so you must notice that it exists. This part is just calling you that you must exist. There is a noise in this model. It's not always means Y equal FX. Actually, the notice is just call you that you just unconscious it, because for the output, it's not just connected with the input, but also connected with the noise. Here.
Actually, I have besides what you said, there is another point is that the random number generators, about the random number generators. Usually there are many kinds of algorithms to generate random numbers, and in some mathematical model, such as the information that she wrote, that the noise must the noise must be a kind of a certain kind of mathematical possibility distribution. So yeah. So you have to choose the correct random number generator with the correct algorithm to fit your formulational number. What is that correct randomness? So we have many ways to generate random numbers, but there were differences between these methods.
I heard we can't generate the correctly random number.
Yes, there's a kind of simplification. So you have to choose the most suitable method for your simulation.
Well, I think here
And usually
We can choose appropriate for target.
Yeah.
I think here they are talking about the following. You have a model and you need some kind of, you need to generate some random numbers. Let's say you need to generate a number between 1 and 6, like dice. The thing is that you should generate, if you're simulating a dice, you need all the numbers with the same probability, right? But if you make a mistake and you put the simulator wrong, and you always generate, for instance, the number 1, your model still works because 1 is a
output for a dice. So the model still works and your simulation runs and you get results, but the model is wrong because that probability is wrong. So the issue here is that even if the model runs, it may have mistakes related to probabilities. So this is a very delicate issue, very difficult to detect.
Thank you very much.
So next, I will talk about validation. It's totally different with the verification. The validation is check whether a program looks at the target as in real world. Once we set a model, we can go to our output. We compare this output with the reality status. So this is a process about validation. And for
So please return to the slides that have two graphs like this. I think it's two second or third.
here,
Yeah.
this part here.
So in the second graph, can you show me where what is the verification process and what is validation process?
It is not included in this graph. Maybe I can write another graph to because it's just from the model to get the simulation data, but it's not included the simulation data to compare with this data. This part with is a validation. We check from here, here, and here, and right or wrong. This is a precise verification.
For example, check the similarity between the simulated data and collected data. What, is this a verification or validation?
You mean compare the simulation data with the
Collected data.
with the data?
With collected data.
Here.
Yeah.
This is a validation.
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 Okay.
What is the verification?
Verification is check the model is right or wrong. Check model is right or wrong from the target to the model. Maybe the abstraction is so abstract. It's better for us to get a more detailed model. When this time, it is called the verification.
So let me see, if it is like you verify the model and you validate the data.
Yeah.
Okay. Are you sure?
I think the most different is the first step about validation or verification. That the objective of that is to make sure the simulation program works as we thought,
As expected.
as we expected. And for another one is that we like to make sure that whether the simulation model fits the reality.
Okay.
So I think it's not the reality. Fits what we want to learn.
Target
So
system.
the target is not the reality.
It's hard
Yeah.
to prove the reality.
So we plan to study this target, and the model. With the model, is it a good model or bad model? Which means it is suit the target or not, not the reality, because we cannot simulate the total reality. Yeah.
Can I get the corrected data before simulation?
You can get the correct data before simulation. You mean the collect data from the target or from the reality, not from the output?
But in many cases, in our lab's research,
Yeah.
we don't know corrected data is not
Collect data.
About
Yeah.
is not conclusion.
This is very hard because we must instruct to the
field we interested, and we collect. So many industry or company not want to give the data. It is difficult.
あ、俺勘違いしました。そのコレクティブデータっていうのは、
わかりますわかります。
鳥貝さんの例でいう、例えば作業員が何人いるかとか、日本語に申し訳ないんですけど、であって、なんか結果ではないんですね、コレクティブデータって。
何が言いたいかわかりますけど、確かに今の研究の内容は、シナリオを使って実際にこれは実現できるかどうかまだわかりません。そういう問題ですか。
はい、妥当性を取るときに結果をシミュレーションしたデータ、シミュレーションしたデータってそれデータですか？結果じゃなくてデータですか？使うデータの話ですか？違いますよね。
データというかシミュレーションの結果。
結果だけで、取れるのはマクロなフィッティングだけで、メカニズムのパラメーターを取る。
中身を取るみたいな構造。
まあ、デク先生よく言ってるけど、データフィーディングは要はそれが目的ではなくて、それをフィットしたから何が分かった、その中のプロセス、そのマイクロのプロセスでその勉強したい、ソーシャル、要は社会現象を、その中身を知りたいわけだからで、あくまでもそのトータルでデータ合ってるっていうのが、それは最終の目的ではない。
So for the simulation, we want to get the process, not the prediction.
じゃあコレクティブデータっていうのは、その途中とかシミュレートデータっていうのは途中の行動の話なんですか？最終的なアウトプットはまだ知らないことを知りたいからシミュレーションするんですよ。
でも現状のデータとかは集められるんじゃない？現状の結果今こうなってるっていうのをシミュレーションでそれを再現してそこでフィッティングかけて、でそこでフィッティングかけられたら別のシナリオとかも入れられるみたいな。
まずはそのモデルは
現状と合ってるか、
現状に合ってない限りまずは間違っていると。
現状実際の世界で起きていることの結果っていうのが一応データとして取れるはず、
ある程度そう別に 100% ではないんですけど、ある程度トレンドとか合っているとそのモデルの妥当性が言えるということで、新しいパラメートとかインプットが入れることで、
鳥貝さんのだったら現状で作業時間がこんぐらい工期がかかってるとかっていうのはデータとして決めて、そこにまず現在の状況のシナリオを入れたら、そことは一致するはずみたいな最初。その後に人を減らしたり増やしたりとかで変えられるよみたいな。
こういうのも前の小沢先生の講義の時もあったんだけど、モデルの結果がデータコレクタッドデータで証明されても、そのモデルはそのモデルは限らない。他のモデルがあるかもしれない。だけどもそのモデルが一応例えばコレクトデータに合ってるんだったら、そのモデルが要は good not bad というそういうバリデーションの価値がある。そのモデルしかないという限らないわけ。他のモデルで反証される可能性もある。だから最終科学哲学的にはモデルが一つという存在ではないので、だからこのモデルはベストというのはないんですよ。だからグッドなのかベターなのかっていう、それを評価するためにはモデルバリデーションというプロセスがある。ベストはないわけです。モデルは反証される可能性ある。他のモデルでも同じデータをフィットする可能性もある。
多分仮説ゼミで天動説と地動説天動説をもとに終点円とかで計算したモデルって洗練されてて、実はかなり正確に予測できたんですね。でも 一動説の方が優れているとされるのはなぜかというと、要するにまあそれがまあより本質を表しているから、だから結果が合ってればいいというものではない。
一ノ瀬の方がより広い範囲で妥当性が取れるから正しいんじゃないですか。
シンプルだからまあいろいろまあそこら辺は多分出てきます。
なんで教科書が買うから出てこないか。
For the validation, I want to ask you to notice this part. Both the model and the target precise are likely to be stochastic and sensitive to slight change in the initial condition. I will talk about this part later. And the model cannot produce some aspect of the target. Model may be correct, but the data are incorrect. So that is why we must use the modification before the validation. And the model is too abstract to validate by the data from the target. For example, such as the artificial society. Once we set the artificial society, we can do a lot of actions from the artificial society. That is not well decided initially. And this is, I will talk about the sensitive analysis. After the modification and validation, we will check whether the behavior of the simulation is sensitive to the assumptions which have been made. They have three precise. The first, various conditions returned in the simulation and observe difference in the outcomes.
So
I think
it is
it's
the
clear.
verification process?
No, it's not the verification or the validation. All you can see, it includes two of them, like both of them. Actually, this is an individual part. You can think this part exists in both of them or depart with both of them. For the publication, once we cite our programs, we may publish the results, leading them to a stock of scientific knowledge, so that other researchers can validate and verify your research. This part is totally clear. So conclusion of chapter 2. What we can learn from the chapter 2? First, concentrate on using simulation to develop theory and form new principles instead of seeking an accurate model. This is what Huan-Song has said. We must put the emphasis on the process. We cannot get the best model, but get a good model to more appropriate to the reality. And the second one, simulation tend to iterate between inductive and deductive and inductive. First, we set an assumption and use the deductive to get to generate some data. And from this data, we compare it with the reality to get our theory. Is the process of inductive. And the model is just like a recircle on the deductive and inductive and more deductive, like a recircle. And sensitive analysis is really important for our model. The last one, develop models of artificial society to investigate not only our present society but also possible social world. This is most important, especially for our life. So for the chapter 3, they will talk about the methodological recommendation with respect to the number of parties to the simulation. I will give us a simple brief about.
Can you explain the number 4?
Number 4, develop models of artificial society to manage. It's not our favorite society, but also. Such as first we set a model base, and we set a lot of scenarios. But these scenarios is not real exist in the reality. But the base is reality. So the base is our present society. After we set some scenarios to, we can research the possible social world. That's the possible exist in
Well,
the future.
this is very important point, as Professor Deguchi always says this, as is and to be.
Yeah.
So, yeah.
So this is most important, especially for our life.
So as is means the present society, and to be is the possible society world. It means what it should be and what. Yeah.
So next part, give a short brief about system dynamics. What is system dynamics? System dynamics is a methodology and mathematical modeling techniques. As is known to all, if we want to set a model, we can set a simulation model or the statistics model. Especially for the statistics model, we use a lot of equations to describe the problems, especially about the model. The actual state of target system, we use the models to get the future state of target systems. When we want to describe the system, especially for us to use the method of system dynamics, we can set a series of equations. The equations can be divided into two series. The first is difference equations, and the second is differential equations. Do you have any questions? I think it's not hard to comprehend, because we always encounter the differential equations and differential equations. And I will talk about the relationship between the difference and differential equations. When we describe the models, we use both of them, but they are not totally different. They have some connections. From the definitions, we can get that this one is differential equations, and from these equations, we can get the difference equations. This is a connection between both of them.
日本語わかります？リファレンスイクエーション。リファレンシャルが微分方程式ですね。リファレンス。
Difference equations.
他の方。差分ですね。差分方程式。
でも連続時間でやることってあるんですか？
ああ、SD は連続ですよね。
これってオイラー法で呼んでるやつ。
まあ、そうですね。まあ、オイラー法は数値計算
ですけどね。随分僕なんかプログラムでお世話になった手法なんです。日本語ですいません。
でもわかります。近似すると。
はい、そうですね。ドライビングシミュレーター、シミュレーター、エニシミュレーター。
数値計算としてオイラー法はあんまりよろしくないので。
Maybe better limited is better than Euler.
そう。多分これから質問モデリングやってみよう。マットライトことあります。
So I will finish my part and about the methodology, about how to set a model. We'll talk about or we'll talk by example.
For the system dynamics, we can see we can model it by equations, and besides that, we can use some diagram to represent the interdependencies of the attributes of a system. So this diagram is a typical system dynamic diagram. So we use this square to represent the stock, which is the accumulated value will be changed over time, and this rate will change the flow here, and this is the supply flow, and the dot line represents the control flow. Sometimes you can see here is a feedback loop. So basically this cloud shape represents the supply, the resource of this whole system. So it is outside the boundary of the system. And then this flow will go to the value of inventory, and the value of this one will be depends on the order rate. So the order rate actually does not depend on the previous value, but depends on the current value of the inventory and some other control variables such as desired inventory and adjusted time. So this is typical system dynamics, which there is a feedback loop. That means depends on the current state, we can decide the next state. And for the software to simulate the system dynamics, the most famous, maybe the first language especially designed for the system dynamics is Dynamo. Actually, this Dynamo can handle an arbitrary number of equations. So here is an example of the previous diagram. This is the Dynamo code. So here for the levels, for the stocks, this is the levels. And the inventory K equals to the inventory J plus the change during the period. So actually, in Dynamo, the time is reflected as this one. K represents the current time, and J is the previous time, and L is the next period. So the time interval actually is the same. And then for the order rate, it depends on the desired inventory minus the current value of inventory divided by the adjustment time. And also we can have some constants in the Dynamo, like we can assign value 6,000 to the variable desired inventory. It will not be changed. And we can also give initialization to the variables, like inventory, the initial value is 1,000. So in this chapter, they use an example called staffs, hawks, and law of binders to demonstrate the system dynamics. So this model is developed in 1986 by this person. Actually, it's a formal model of the Hobbesian state of the nature from the bioeconomics perspective. So what is Hobbes' state of nature? Basically, in this nature is a society, and all the members of this society will compete with each other for some resources. And all the resources belongs to some members, so there will be conflict between the owner of the resource and the person who wants to have some additional resource. And basically, there are three strategies: the dove, the hawk, and law of binders. Am I speaking too fast? So for the three strategies, for the dove, actually from the name we can see it's very peaceful. So the dove will never try to get others' resources but waits for them. And also the dove will give up their own resources once being attacked. So if two doves compete for the same resource, then with equal probability they will get resource. And for the hawk, actually is very aggressive. It will try to get other members' resources, and they will never give up their own resource unless they hurt seriously. And for the law of binders, it's similar to the doves. It never tries to take others' resources, but wait for them. But different from the dove, it will defend its own resources unless it succeeds or be defeated. So in this part, the law of binder is kind of combination of the doves and hawks. It takes both of the advantage. So for this system, what is the purpose? Actually, we want to try to figure out which is the most profitable strategy. So the most profitable strategy will be transmitted among the populations. So how can we model this one? So we need some payoff table. So we define a variable Rij as the gain of the individual following strategy I. One, this individual means another individual following strategy J. And this one is calculated as the utility of the resource minus the cost of fighting and waiting. So for the notations, we use E to denote the utility of the resource. CH denotes the cost of fighting, and CD is the cost of waiting. So according to this strategy, we can have a payoff table. So here, for example, when two individuals with the same strategy meet with each other, they will get the results with equal possibility. So for example, if a hawk meets another hawk, so one of them will get the utility and one of them will be hurt seriously. So one of them will get U and another will get CH, the cost of fighting, right? And because they are with equal possibility to get the results, so it's divided by 2. And for example, maybe for the doves, if a dove meets another dove, then they have to wait, right? So it will be U divided by 2 minus the time of waiting. So for the law of binders, if a law of binder means other individuals, it may depend on who is the owner of the resource. So for example, if a dove meets a law of binder, if the owner of resource is the law of binder, then of course the dove will get nothing, and the law of binder will keep the resource. But if the owner of the resource is the dove, then with equal possibility they will get the resources. So that's why it's U divided 2 minus CD. And then with equal possibility is divided by 2. So similarly, we can derive this payoff table based on the previous strategies. And here we assume the utility of the resource is smaller than the cost of fighting, but larger than the cost of waiting. So we can assign some concrete values to the payoff table, like we can assume the utility is 10, the cost of waiting is 3, the cost of fighting is 20. So we can derive a concrete payoff table, which can be used later for the simulation. So, is there a question?
Is there any relation of inventory model and this?
No. Inventory model is very simple. It's only try to figure out what is the value of this one through time. So there is no game. There is no many individuals.
Defined model.
Yeah. So for this one, it's quite complex. We have different strategies. So how we can evaluate this strategy, we need some payoff.
But this model is also
system dynamics. So we can use mathematical equations to model the system dynamics. So for this one, the growth of the subpopulation with the strategy I actually is modeled as proportional to the difference between the average gain and the overall mean gain of all the strategies, depends on this function FIT. So for the YIT is the average gain of an individual applying strategy I at time t is calculated as the sum of the production of this RIJ, which is the entry of the payoff table, times the proportion of the population which applying strategy J. So this is the average gain. And the mean gain of all the strategies, we sum the product of the average gain of strategy I and times the proportion of population which applying this strategy. And then we can guess the relative growth of strategies as this formula. That means the population of strategy I depends on the current population of strategy I and a change rate. And then we can, according to the previous equations, we can transform this equation this difference equation to a differential ones, and then we can have a relative growth of the strategy. I think it's quite straightforward, so I will not go into the details. And then there are many different ways to evaluate these differential equations, and one of them is the linear stability analysis. For this linear stability analysis, it means we focus on whether and where the system has a stationary state. For this stationary state, that means it is a state. Once the system reaches it, will remain for a while. So it also focuses on whether or not it also focuses on how the system performs within a small region of the stationary state, whether it's stable or not. So in order to carry out this analysis, we allow the left-hand side, the right-hand side of the equation equals to 0. So there are 4 candidates of this stationary state. The first 3 is that if we assume the whole population actually applies with the same strategy. For example, we only have the law binders and we don't have dove and hawks. So if we apply this value to this equation, we can see it's always true. As the fourth possible stationary state is that the doves and hawks actually coexist with each other without the law binders. So if we evaluate this equation, we can have the proportion of dove as this one, the proportion of hawks as this one, and without any law binders. So then after some analytical treatment of the equations, then we can show that there is only one stable state of this system. That means only the law of binders actually is surviving without any doves and hawks. So next, I will carry out the simulation, then we can see this result. You can see this stable state. So, any questions? Of course, we can use a dynamo model to simulate the system. We can convert the equations to the dynamo code easily here. But the problem about the dynamo model is that it does not reflect the fact that the population actually is constant. And also the individual flows between this population cannot be modeled. And we also cannot determine how many individuals actually change their strategies. So that's why we do not use dynamo model in this case. We use another software called Stylo. Actually, it's a software package for system dynamics as well. But for this one, the free version of Stylo is save disabled. So even I run this code, I cannot show it here because I cannot save it. And also, they cannot run on the Mac OS level. So I will only show the output here.
Well, I think in our lab we have a license for Stylo.
Really?
It's somewhere in the self case.
Really? Yeah. But if we have license, you can try it by yourself. It's very simple actually. The Stylo starts from the diagram. So first of all, you draw this diagram. Here we can see there are 3 levels, 3 stocks: the doves, the hawks, and law binders, and some control rate here. And for all those other circles, there are some attribute factors which will help the calculation. And then after you draw this diagram, the Stylo will convert this diagram into some mathematical equations. And of course, for the right-hand side, you have to type in by yourself, but it's not very hard based on the previous math equations. And then by giving different initial values, we can see the output. We can see how the population changed. So if we have 90% of hawks initially, then we can see the number of doves, this blue line, increase and decrease until there is no doves. And for the hawks as well, it will decrease slowly. And for the law of binders, the number of law of binders will increase slowly up to certain points until it occupies the whole population. And if we have 99.9% of hawks as the initial value, then we can see the number of doves actually increase to a certain point and then remains stable for a while and then decreased to 0. And also the number of hawks decreased to a certain level and then remains stable for a while and then decreased as well. So here actually is a stationary state, but it's not stable. So later they will change to 0. And for the law of binders, you can see it only prevails after a certain point, maybe after time 20, and then will increase quite fast until it occupies the whole population and continuously. So actually this one is a stable state because it will not be changed at all no matter what is the initial value. So what we can learn from this result is that the law of binding strategy only prevails after a certain time. And the larger the initial proportion of hogs, the longer and more sudden it takes for the law of minors to grow. So we can see if we have 90% of hogs, it will increase at the first beginning and is quite slow. But if we have 99% of hogs, it will wait until time maybe 15, 16 to increase, and increase quite suddenly. So that's the difference. And also we can initialize 90% of doves. Then we can see a similar result, that the number of doves decreased to a certain point and remain stable for a while, as the number of hogs increased to a certain point and remains stable. And then the number of log miners will wait until a certain time to increase until occupies the whole population. So here is also a stationary state, but it's not stable. So we can see no matter what is the initial value, the law of miners will necessarily prevail because of its ability to inherit, to imitate and learn. So from the mathematical equation, we know there is only one stable state, but we do not know how the flow changed between these subpopulations. So by the simulation, we can see how the individuals changed with strategies along the time going. But for the simulation, there is one problem, because every time we can only have one initial values, right? So in order to generalize the conclusion, we have to run multiple runs of the simulation. So in this paper, in this chapter, after multiple runs of the system dynamics, there are two conclusions. One is that in a more homogeneous population, that means only a large majority of doves and hogs, the law-abiding strategy will only prevail after a certain time. As the later it succeeds, the more sudden it will grow. And also in a mixed society of hogs and doves, the law-abiders will begin to multiply very fast. So this is the conclusion of this example. And then
why did this model didn't occur the vibration in the
I think it depends on the mathematical equations. Because we model the system in this way, and we can derive some differential equations. And then through the analytical treatment, we know there is only one stable state, but we do not know through which process we can achieve this stable state. And then by the simulation, actually this simulation represents the cases of
in the
this
likely
game.
model, Lotka Volterra equation in the
Sorry, can you say it again?
ノート結構発音わからない。プレデターなんでビクティブ。
No, it's just we want to say how the subpopulation changed under this game, how the individual changed their strategy to get a better payoff.
So simulation is useful.
Yeah, that's right. So it's kind of we can see it from the payoff table. The hogs, of course, they will get the resources, but actually the cost of fighting is very large as well. So they will lose many points. And also for the doves, although they do not try to get others' resources, but they will not get the resource as well. Right?
Yeah, if there is no low abider, there would be
even there is a small portion of the low abiders initially, then actually the population will increase until it occupies the whole population, because this strategy is much better than others. So actually there is another model called word models. It's a system dynamic as well. And Forest word 2 model is the first and simplest of such word model. But we can see actually its stellar diagram is still very complex. So I will not go into the detail of this one. But still we can see there are 4 sectors: the population sector, capital sector, natural resource sector, and pollution sector. So each of these sector has 1 or 2 internal feedback loops, and they are connected together by some vectors. And then for the word models, we try to predict the population of the word. So the population will increase and decrease depending on the birth and death rate. And then the birth rate actually depends on the actual population size, this one, and some normal birth rate, and some other factors like food supply, materials, life standards, clothing, and pollution. So for these last 2 terms, the value of these 2 multipliers will be determined by table functions. So what is table function? Table function is used in Dynamo to model the linear relationships between 2 variables based on a large amount of empirical data. So in this model, there are 22 table functions and includes 151 numerical values. So in certain cases, the table functions can be very dangerous. Actually, we can see it from this diagram. This diagram is a reproduction of the word 2 model back to 1880s. That means based on the current population, we try to predict the past. So we can see here, according to the simulation, in 1900, the population decreased from 6 million to 1.7 billion. Sorry, from 6 billion to 1.7 billion here. But actually, this is not the real case. Actually, in 1900, the population is around 4 billion. So there must be something wrong here. And then later, some other researchers changed the value of the table functions and get a better result. So that's why the table functions can be very dangerous, because the table function is just a rough method to represent the dependence of one variable on the other one. And also sometimes the modelers only have a wrong idea what the dependence means. And also sometimes the solution of the linear dependence might be very different from the solutions of nonlinear ones. Although the linear ones is much easier to be tracked by mathematical equations. So this problem is called the trap of tractability. And also there are other problems of the word 2 model, like in this word 2 model, the population is treated as a whole and the age structures is not considered. And also the difference between different countries are not considered as well. And later some other researchers built some better models to give attributes of different countries, but they are not system dynamics at all. So this shortcoming reflects some limitations of the system dynamics as well. Like system dynamics only describes the target system as a whole, as a single entity, and we cannot divide the system dynamics. So if we want to learn the attribute of a particular part, we cannot do it. So we have to use some other simulation techniques, like maybe multi-agent based simulation, which will be introduced in later chapters. So that's all about my presentation. Any questions about system dynamics?
成長の限界って聞いたことあります成長のローマくらい、
崩れると
昔そのフォレスターのモデル使っている人口の成長がどっかの限界に達すると結局外れたんですけど
その当時はすごいインパクト
非常にブームだった。
それがあれ使ってたんですか？
このモデル。
でシステムダイナミックはブームだけど。
If you are interested, you can try to write it yourself. It's very easy. It's only take half an hour.
2000度かなんかにそれが載ってた気がなんかそれでなんか70年から2000年ぐらいまでなんか一致してるとかなんか
Press that once in there. When is the peak? When is the peak of population in the graph?
Year 2013.
2030年が成長の限界
でこれからですか。
でなんかどっかで見た。
2021.
昨日ですよ。
I'm not very good.
人口とかいろんなものが美しい。
Thank you very much.
最後のラストスライド。What does it mean a system dynamics model is an individual fold?
That means we can see. Actually, I can use this. So this is a system dynamics. So the major purpose is to try to evaluate the value of these stocks, and this stock has several attributes. So we cannot divide this system, right? And if, like for the world population, so we simulate the population as a whole, right? So actually in this population, different countries will have different attributes, right? Like maybe for the Asia, the attribute will be different, like US, Europe. Different countries has their own attributes. But in system dynamics, we can only to evaluate this whole population. If you want to understand the population of Asia, population of US, and what is the interactions among them, we cannot use system dynamics. We may use some other simulation techniques. So, Hope actually is a whole population as well. Then there are subpopulations. And for different stocks, this is the stock. And all the attributes actually are the same, right? So the attribute actually is given to the whole population. And according to those attributes, there will be individuals selecting this one, selecting this one, selecting this one. So there will be a flow within the system. So actually, they are only applying different strategies, but basically they are still the same. It's not like this one. This one is like they have different attributes. The strategy for this one is unique for the whole system. Right? The equations actually the same for all the different parts. So the purpose is try to understand the flows among the population. For this one is different entity within the population. So if we want to understand this one, we have to divide.
Could you give some conclusion remarks of chapter 1 and 2 if possible?
Chapter 1 is chapter 1 is about what is simulation and why we have simulation, and also gives a short brief introduction of there are many different techniques of the simulation, right? And then chapter 2 talks about the whole process of the simulation. First, we will have a real phenomenon, and then we try to abstract it to a target system with different attributes. And then through the simulation, we can get some results, and then do verification and validation to make sure our model is good, right? And we can also do some sensibility analysis, which means we try to test whether our model is robust or not, right? And then chapter 3 is about system dynamics. And system dynamics is very useful, as we can see, to simulate the flows, to simulate the feedback loop among the system. But I think there are 3 basic techniques of simulation. One is system dynamics, one is agent-based simulation, one is discrete time simulation. These 2 actually are very popular, and there are some similarities overlapping between these 3, but actually in certain cases they are different. So it's like if this is the system dynamics, this is the agent-based simulation, and this is the discrete time simulation, if I remember it right. So these 3 are actually the most popular ones. Discrete time simulation. I have a paper talking about the difference between these 3.
They call it a triangle
maybe
social simulation.
Maybe later I can upload the paper talking about this one. Actually, it's a very easy reading paper. Talks about the difference and the similarities. So maybe in later chapters we will talk about agent-based simulation.
So you are the first group of this book seminar. So could you tell us what is the hard point on work group, and what is the point to work group? Any hints or any suggestions on work group?
So I'm not clear about what you want to know, because this includes a lot of things.
I don't know. I would just, if possible, you can give some hints on group work.
Group work.
Yeah.
Start earlier. Start earlier, do not wait until the last minute. Then you can have time to discuss, right? If for the individuals before the deadline they finish their own part, then there is no time to discuss, right? And I think discussion is quite important, especially each group there is a doctoral student, right? So if the master student, so if for the master students they have any question, they can ask, like in Guino's group, they can ask, right? So they can understand the materials.
Okay, thank you very much.
So point is to start earlier, do not wait until the last minute. Thank you very much.
You have any questions or comments? No. Thank you for your presentation. The next presenter is Group 2. Oscar, Iwashi.ツイッターとかなんもない。あれ順番はどんな感じ中で？
五十嵐さん、もやさん、俺、オスカーだった。
なんで最初電話しなかったそれってあいつファーストバッターチェアマンです。
じゃあ 10分休憩します。あ、5分休憩します。
5分休憩してどうするんですか？
とりあえず五十橋君と連絡を取っていきつつ、トイレ休憩で。
これから発表する。
まあ、5分で何もならないです。
まあ一応確認
わかりました。
でその間にグループ内でどうするかも一応話してください。5分。じゃあ50分から始めます。
どうぞちょっと電話してもらっていいですか？
あ、俺電話する。
大規模な、まあ